Welcome to Animal Cognition Lecture 4. This lecture is going to be in two parts. And in the first part, we're going to be discussing what is learning and why learning evolved. And we're going to distinguish between operant and classical conditioning. But the focus of part 1 is going to be on classical conditioning, its basic components. And we're also going to discuss what is required in order for classical conditioning to take place. And there we're going to focus on two factors, contiguity and contingency. And what we're going to see is that rather than being a mere behaviorist process, that classical conditioning involves a cognitive dimension, right? It assumes for it to take place that the animal has some cognitive abilities and it's not a simple stimulus response machine. So let's begin with a definition of learning, right? As I state, learning is a relatively permanent change in behavior that results from experience, right? So as the animal is interacting with its environment, right, having some experiences, it acquires some information that it can carry through to other future situations, right, and allow it to respond adaptively. And, well, why is learning important, right? Why is it that an animal can just not rely on instincts to solve all of its problems? Well, the reason is because natural selection can't build in everything that an animal needs to know in order to survive and reproduce, right? So, for example, where food is available, right, is something that can change from generation to generation, right? Even within the lifespan of an individual animal, where food is located and the kinds of things that it can eat can change. So it can't rely on a simple program built in by natural selection to figure out where food is. Right? So another way of saying this is that natural selection requires environmental consistency across many generations, right? The same factors have to be at play with each subsequent generation in order for a solution to be achieved by natural selection. Right, so things that change a lot within the lifespan of an individual animal or between generations is something that would benefit from learning mechanisms and not just simply instinctive responses. Now, there are two kinds of learning that psychologists of the behaviorist tradition distinguish, right? Both allow an animal to learn important associations between events, and one of these is operant conditioning and the other is classical conditioning. In operant conditioning, animals learn how to manipulate the environment to get something they want or to avoid something that they don't want. Right? So they learn the consequences of their actions, that these actions in these circumstances either lead to something they want or they don't want. And an example of this is the spider Portia fimbriata that we discussed last time. We said that when it encounters a novel spider, right, when it invades the nest of a spider that it's not familiar with, it adopts a trial and error strategy, right, vibrating the web in such a way that it starts off randomly generating a certain pattern, and then depending on the consequences that this has for the behavior of the resident spider, that pattern of vibration either becomes more or less common. Right, and so that's operant conditioning, right? They learn how their actions affect the environment. Classical conditioning is a little different, right? Classical conditioning allows animals to learn about cause-effect relations in the world. Right? It learns that one event typically follows another. So an animal may learn, for example, that a certain sound, like the sound of a chainsaw, is followed by a tree falling down, right? And that might help it to clear out of the way. So as I said, in this part, we're going to be focusing on classical conditioning, and in the next part, we're going to focus on operant conditioning. So in classical conditioning, animals learn that one event foretells or predicts the occurrence of another event. Right? They learn that one event is followed by another. And another way of saying this is that through classical conditioning, animals learn to detect causal relations. They learn to detect that one event causes another. Now, this is not the same thing as saying that they learn to understand these causal relations. Right? Knowing that one event follows another, or one event is caused by another, is not the same thing as knowing why that causal relation holds. Right? To understand causal relations, right, they would need to know the mechanisms that link the two events. And no one is saying that animals understand these relations. And humans, in many cases, know that things are causally related without knowing necessarily why they're causally related. One of my favorite examples of that is the TV remote. I know that when I hold the remote in a certain direction and press a certain button, that it turns it on. But I don't necessarily understand the mechanism by which pressing a button happens to change the channel or raise the volume, right? So I know the causal relation without understanding it. The first person to really focus on operant conditioning was Ivan Pavlov. I'm sure you remember his work from either the learning course or your introductory psychology class. He discovered classical conditioning while doing research on the physiology of digestion. And he actually won a Nobel Prize for figuring out how to perform a surgery on animals whereby he could collect stomach juices through a hole in the abdomen without killing the animal. Right? And he had other methods for collecting saliva, for example, including from the mouth of the animals. And in one study, he was examining saliva production using dogs as subjects. So he used dry dog food and he recorded the amount of saliva that was produced. And the food was brought to the dogs who were harnessed in the lab by an assistant. And what he noticed, because he's recording salivation, right, he noticed that eventually the dog started to produce saliva at the mere sight of the assistant, even if no food was actually presented. Right, so he called that classical conditioning. And there's 4 important components to classical conditioning. There's the unconditioned stimulus, the unconditioned response, the conditioned stimulus, and the conditioned response. So let's start off with the 2 unconditioned components of classical conditioning. Unconditioned means unlearned. Right? So the unconditioned stimulus is a stimulus that naturally or automatically produces a specific response on the part of an animal. So for example, dog food might be an unconditioned stimulus in the Pavlov case. And an unconditioned response is the response that happens automatically when the unconditioned stimulus is presented. And an example of that in Pavlov's case would be the salivation when dog food is presented. Right? And the production of saliva on the part of a dog helps them to chew and swallow the dry dog food. So we can think of the link between the unconditioned stimulus and the unconditioned response as being like a reflex. One automatically produces the other. Now, as I said, there's 2 additional components to classical conditioning, and this is the conditioned stimulus and the conditioned response. And the conditioned stimulus is an initially neutral stimulus. Right? It's a stimulus that doesn't on its own produce any particular response. So in Pavlov's case, the presence of the assistant, for example, would be the conditioned stimulus. It acquires the ability to elicit a response only once it's paired with the unconditioned stimulus. And the conditioned response is the response that's produced when the conditioned stimulus is presented after conditioning has already taken place. Right? So, for example, salivation to the presence of the assistant would be a conditioned response. It's a learned response to the conditioned stimulus. So the idea behind classical conditioning is that when you pair a conditioned stimulus with an unconditioned stimulus, eventually the conditioned stimulus on its own comes to elicit the conditioned response. Right? So you start off with a stimulus that naturally elicits a particular response, and then you pair the initially neutral stimulus with that unconditioned stimulus. And as I said, eventually the CS itself comes to elicit a conditioned response. Right? And as we'll see, what is learned is that the animal learns that there is a predictive relationship between the conditioned stimulus and the unconditioned stimulus. Right? The conditioned stimulus predicts the unconditioned stimulus, and they produce the conditioned response in anticipation of the unconditioned stimulus being presented. Now, I want to also discuss some important extensions of classical conditioning, right? Some other concepts that are associated with classical conditioning. And one of these is the concept of extinction. Right? And this is when a conditioned stimulus no longer produces a conditioned response. Right? And this happens if the conditioned stimulus stops predicting the unconditioned stimulus. Right? So if the two are no longer paired, eventually the conditioned stimulus on its own won't produce the conditioned response. Right? And that happens if it's not paired after many trials. Right, so if the assistant shows up at the lab no longer bringing food and does this repeatedly, then eventually the dogs will stop salivating at the mere sight of the assistant. Right? Another important concept surrounding classical conditioning is the idea of stimulus generalization. Right, this is also something that was discovered in the lab. And this is when a conditioned response is produced to stimuli that are different from those used during conditioning. Right? So sometimes stimuli that are similar to the conditioned stimuli begin to elicit the conditioned response, even if they weren't used during conditioning. And, one question is, well, why would animals and humans be built to feature stimulus generalization? Well, because it's adaptive, right? Stimulus generalization allows animals to be more flexible, right? More flexible in their behavior. Right? And the reason for this is because what's useful, a response that's useful to one stimulus is likely to be useful to a relevantly similar stimulus. So let's say that an animal learned to fear one animal with big teeth, right? Generalizing that fear to other animals with big teeth would probably be adaptive as well. So those are the components of classical conditioning, and we also discussed stimulus generalization and extinction. Now I want to focus on what is required for classical conditioning to take place. Right? Under what conditions does it occur? And according to Pavlov, the only thing that's important is for there to be a contiguity between the conditioned stimulus and the unconditioned stimulus. So what does this mean? What is contiguity? Contiguity has to do with how closely associated together in time the two stimuli are. Right? Animals learn to associate two events because they're presented closely together in time. Now, what's important about this definition of contiguity is that it doesn't specify an order. Right? It doesn't say that the conditioned stimulus always has to appear before the unconditioned stimulus. Right? They can occur either before or after. Right? All that matters is that the two appear closely together in time. Well, is that true? Right? Is contiguity sufficient for classical conditioning? And this idea was tested in a classic experiment by Rescorla using what's called the truly random control technique. Right? So he tested the idea that just having contiguity is enough to produce classical conditioning. And the study used rats, and the unconditioned stimulus was a mild shock to the feet, and the conditioned stimulus was a light presented in the enclosure. And he compared two groups of rats. Right? One group he called the standard group, and the other group he called the jumbled group. So let me define what those two conditions, or what those two groups were. In the standard group, the conditioned stimulus was always presented before the unconditioned stimulus. Right? CS always came first, then the US. And in the jumbled group, the CS and the US appeared the same distance apart in terms of time as in the standard group, but the order was randomized. So sometimes the conditioned stimulus came first, then the unconditioned stimulus. Other times it was the other way around. So both of the two conditions, the contiguity is the same. Right? The amount of time separating the two stimuli is the same. The only difference is in whether in one the CS consistently precedes the unconditioned stimulus or whether it's random. Right? If contiguity is all that matters, right? Because the contiguity is the same in both cases, you should find that the same conditioned response is produced in each case. Right? Both conditions should yield classical conditioning. And in this case, the conditioned response would be freezing, right? Which is part of the natural fear response of the rat. So what he found was that the rats in the standard group came to produce the conditioned response to the presentation of the light. Right? So when they saw the light on its own, they came to produce the conditioned response of freezing. But the jumbled group did not produce the conditioned response in the presence of the light alone. Right? So what this tells us is that contiguity is not enough to produce conditioning. Right? It might be necessary, right? So the two stimuli might have to appear closely in time, but it's not enough. Right? What also matters is the order in which the two stimuli appear. Right, so another way of saying that is that contingency is important. Right, that the unconditioned stimulus be contingent upon the previous presentation of the conditioned stimulus. So contingency is when the unconditioned stimulus follows the conditioned stimulus. Right, CS is always first, US is always second. But other research has shown that contingency on its own doesn't always produce conditioning. Right? And so again, another classic experiment, this one by Kamen, called the blocking experiment. And again, he used rats as the subjects. And the rats were either assigned to the experimental or the control group. So let's examine these two groups. There's 3 phases to the experiment. And for the experimental group, in phase 1, the rats were trained with a buzzer as a conditioned stimulus and electric shock as the unconditioned stimulus. And the response was the startle response. So again, freezing. Right? So the CS is the buzzer, so the buzzer happens, then electric shock, and then we see the response, the startle response. The control group did not participate in the phase 1, right? They didn't undergo any kind of conditioning. Now, phase 2, both groups were trained with a complex conditioned stimulus. And what that means is that the conditioned stimulus had two components, right? One was the buzzer, exactly the same as in phase 1, but this time it was also paired with the presentation of a light. Right, so you got a buzzer and a light, followed by a shock. Right, and again, both groups underwent that in phase 2. And in phase 3, right, both groups were just presented with a light, and he measured the degree to which they produced the conditioned response of freezing in response to that light. So is there a difference between the experimental and the control group as far as the tendency to feature conditioning to the light? Right, so the above figure summarizes the methodology for the experimental and the control group. Right, so again, phase 1, there's only for the experimental group, there's a buzzer followed by a shock. In phase 2, there's the light and the buzzer followed by a shock, and then the light test in phase 3. Control group, no training with the buzzer in phase 1. Then they see the same compound stimulus of light and buzzer in phase 2, and then the light test, light on its own, to see if there's a conditioned response. And what came and found was that the experimental group did not produce the conditioned response to the light alone. Right? The experimental group did not produce the conditioned response to the light, but the control group did. Right? They did learn to associate that stimulus and the response. Right? So the control group did learn that light predicted the shock, and that's evident by the fact that they responded with fear to the light. But the experimental group did not learn to associate the light with fear or with shock. So he called this phenomenon blocking. Right, blocking. And that's when an animal, once it's acquired one CS-US connection, cannot acquire other CS-US connections. Right? So having established one connection between a conditioned stimulus and an unconditioned stimulus, it can't learn other CS-US connections. So in the experimental group, in phase 1, the rats learned to associate the buzzer with the shock. Right? They learned that the buzzer is followed by a shock. And having learned that connection, they can't learn that other stimuli are also connected with a shock. Right? They're blocked from making that association, even though there is a relationship of contingency between the light and the shock. Right? So that shows again that contingency isn't always sufficient for producing conditioning if the unconditioned stimulus is already associated with another conditioned stimulus. Right? Of course, the rats in the control group did notice the contingency between both CSs and the conditioned response. They weren't blocked from learning these associations because they didn't already have one to begin with in phase 1. So once Kamen discovered this, other researchers early on sought to examine what do you need in order for an animal to be able to notice an additional conditioned stimulus. Right? And one of the researchers that looked at this was McIntosh. And he argued that for an animal to notice an additional conditioned stimulus, that stimulus has to make some difference in predictive value. Right? So there must be some additional predictive value to that other stimulus in order for the animal to be able to connect it with an unconditioned stimulus. So for example, when the pairing of two conditioned stimuli leads to a stronger unconditioned stimulus, blocking does not occur. Right? The animal isn't prevented from learning an additional association if the two together produces a stronger unconditioned stimulus. So let's say that if you start off with a tone followed by a shock with a particular intensity, let's call it intensity X, and then in the second phase the animal is presented with a tone and a light followed by a stronger shock, right, an intensity greater than X, then the animal can learn to associate light with the shock. Right? So blocking doesn't occur under those circumstances. All right, so to summarize, there has to be an element of surprise for the animal when the initial conditioned stimulus is paired with another one. Right? There has to be some additional, something that has to stand out. Right? Otherwise, it's not going to learn that another conditioned stimulus also predicts the unconditioned stimulus. Right? So it's not going to learn that another CS predicts the US unless that US is somehow different under the combined condition. Another way of saying this is that the animal's expectations have to be violated, right, to prevent blocking and to get the animal to notice an additional stimulus. So if we put this discussion together, what we see is that although initially proposed and championed by the likes of Watson as a purely behaviorist process, right, we see that classical conditioning involves many cognitive elements. Right? It involves animals making predictions and having expectations about stimuli and the causal relations between them. Right? It's not a dumb behaviorist process. It actually involves some kind of cognitive dimension.